Hello students, and welcome to section 6-4, Geometric Sequences. Jumping right into our first example, identify arithmetic and geometric sequences. Is each sequence an arithmetic or a geometric sequence? A geometric sequence, let's start with the definition. It's a number sequence in which each term after the first term is found by multiplying the previous term by a common ratio. We're going to look for a common difference or a common ratio between consecutive terms. As it turns out, this is the only description as far as a geometric sequence goes. The arithmetic sequence will be something that utilizes something called a common difference. Let's take a look. You'll see in the example how each kind of unfolds here. So let me go back to the sequence, 3, 2, 4/3, 8/9, 16/27. So take a moment and think how we are progressing from 3 to 2, 2 to 4/3, and so on and so forth. Are we multiplying by a number to go from 3 to 2? Are we subtracting? Are we adding? Or are we dividing? I guess you can think, though, be careful. Multiplication and division can work together in conjunction, because if you were dividing by a number, it would be the same as multiplying by its reciprocal. And if you're adding by a number as opposed to subtracting, well, you can think of subtracting as simply adding the opposite. So see if there's a pattern there that you can observe. Turns out that if you subtract the second term minus the first, you get -1. So 2 minus 3. If you subtract the third term minus the second, you get a different number. You get -2/3. So this is an example of how the common difference is technically not the same. As a matter of fact, we can't call it common because they're not common. So there is no common difference. So it's definitely not what we say as an arithmetic sequence. What if we took the second term, though, and divided it by the first? And again, this is now going to be called a common ratio if the numbers are the same, which, as it turns out, 2 divided by 3, 2/3. What about the third term divided by the second term? What's 4/3 divided by 2? Well, remember, dividing by a number is the same as multiplying by its reciprocal. So you've got 4/3 times a half. 4/3 times a half, 4 divided by 2, when you flip the 2 as 1/2, turns out to be 2. So 4/3 divided by 2 is simply just 2/3. So these two numbers, because they are the same, we call it a common ratio. And therefore, every single term you can see, and you can test this theory. Move things over for you here. Every single term will propagate in the way that I indicated. In other words, there is no common difference, as I said earlier, but there is a common ratio. And they did one other division. They did 16/27. Actually, they did two more, not just one more. 16/27 divided by 8/9 is also 2/3. And they did 8/9 divided by 4/3, which is also 2/3. So to go from 3 to 2, 2 to 4/3, and so on and so forth. From one term to the next, you're multiplying by 2/3. So the sequence does not have a common difference. Like I said earlier, it's not arithmetic, but it does have a common ratio of 2/3. So the answer, as I said earlier, is, well, just that. It's geometric, and the common ratio is 2/3. So you can kind of see I'm giving up the answer here on the next problem, so let's cover that back up. If you saw it, that's okay. Oops, you saw that too. All right, so this next sequence, 3, 4.5, 6, 7.5, and 9, how do you go from one term to the next? Let's take a look. And again, if you can kind of formulate in your head how it can take shape, maybe subtract 4.5 minus 3, 6 minus 4.5, 7.5 minus 6, 9 minus 7.5. Are those differences common? If not, then test 4.5 divided by 3, 6 divided by 4.5, and so on and so forth, which they do right here for you. Quite nicely, I would argue. And it does turn out okay, that if you do 4.5 minus 3, 6 minus 4.5, every term minus the previous subtracted, you get the same exact difference. So there, as you can see, it is a common difference. All right, so what's the argument? The argument is that we do in fact have an arithmetic sequence. The common difference of 1.5 is what we observed, and then therefore, like I said, it's an arithmetic sequence. The definition up above for geometric kind of takes us back to the title of the lesson. You do need to know both arithmetic and geometric sequences, but this is a nice warm-up to kind of compare the two. Example 2. So we're going to write a recursive rule. A recursive rule is just a fancy way to say how can we, not just in looking at this sequence, which is in fact geometric, how can we describe it with variables? So that instead of asking you for the 1, 2, 3, 4, 5, 6th term, instead of finding the 6th term by multiplying by some common ratio, which is what's going to be the case here, what if I said, give me a situation where I wanted any term, let's say the 10th term, the 20th term, the 100th term. If I asked you for the 100th term here, what would you do? What would you say? Well, recursive formulas allow us to come up with, as it turns out, any term in the sequence. So the first thing you're going to note is this formula. A sub n equals r times a sub n minus 1. And it kind of sort of takes shape, in a manner of speaking, takes shape as a function that you're already familiar with. You don't see an exponent here, but it will appear here in a moment. Let me explain what this is, and I'm trying to give you guys a little bit of a clue as to what it's going to take shape as. Anyways, we'll get there. With regards to what we see, we've got a sub n. This is any random term that you want to call on. Let's say you want to look at the 4th term. So a sub 4 would be 27. Okay. According to the formula, a sub 4, whatever this 4th term is equal to the common ratio times a sub n minus 1. What's a sub n minus 1? It would be a sub 4 minus 1, or the 3rd term. So if this number is 27, this number would be 18. And then 18 times the common ratio, well, you might even be able to do this quickly by dividing 27 by 18 to get that r value. Okay, you are going to get a fraction if you're not already seeing that here. But let's continue just to give you a heads up. Nth term is the a sub n, r is the common ratio, and then the green, as you see, a sub n minus 1 is the previous term. Find the common ratio. So I already kind of highlighted that idea. So yes, 12 divided by 8, 18 divided by 12, 27 divided by 18, and so on. You end up with 3 halves, which is exactly what we need as far as noting the common ratio. Putting it all together, here's your equation. Okay, so a sub n equals 3 halves times a sub n minus 1. Now we did substitute r, or for r we substituted 3 halves. So this speaks to what we would call a recursive rule. The nuance to all recursive rules, as you're going to see a lot, is that if you don't know the first term, then you're not going to know where to start here. So not only is this the answer as far as the formula, you also need to say what a sub 1 is. Or at the very least, I guess, you need to say, if in fact there's one term that helps you find the next term, or 2 terms, or 3 terms, and so on. Later on, we'll learn quite a bit more as far as recursive formulas go. This is just a nice warm-up to the idea of, well, if you know what the first term is, you know a sub 1 is 8, then you can find the next term. In other words, a sub 2 minus 1. Okay, because 3 halves times 8 would of course be 12. So you're finding the second term. If you plug in 2 here, a sub 2 equals 3 halves times a sub 1. So 3 halves times 8 gives you a sub 2, and again that's 12. So you could use this formula to find the next term. Formulas of this nature are a little bit harder if in fact you're finding, let's say, the 100th term, because technically to find the 100th term you still need the 99th term. But that's going to change here in a quick moment. We're going to take a look at the explicit formula. So what is the 10th term in the sequence shown in example 2? So recursively speaking, look at this formula. It does give you an a sub n and an a sub n minus 1 as well as the r value. Let's do the same problem, but watch this. Okay? We are going to start with this formula. It looks similar, but notice there's an exponent here. Okay? So it's not just to the first like we saw up above. This would be to the first. It's to the n minus 1. And look at how we've kind of flip-flopped some things here. The common ratio is the base of this particular exponential form here. And yes, it is an exponential form, if it isn't already obvious. A sub n, it's still the same a sub whatever you're trying to find. A sub 10 is eventually what we'll figure out here. A sub 1 is the first term. And we already know some of these details, right? We know the first term is 8. Right? So a sub 1 is already known. R is also known to be what? 3/2, your common ratio. And they've color-coded it nicely so you can kind of see when things start getting plugged in. So the nth term, so a sub whatever, could be a sub 10, for example, right? Equals a sub 1, the first term, times r, the common ratio, raised to the n minus 1 power. All right, we already knew, like I said, the first term was 8. We knew the common ratio was 3/2, so literally all you got to do is plug it in as such. So a sub 10 is equal to 8 times 3/2 to the 10 minus 1 power, which is 9. And then you just use your calculator and look at that. I would definitely not suggest that you use the recursive rule, although you could, right? You could go back on the last example and you could theoretically take 40.5 multiplied by 3/2, whatever that is, times 3/2, times 3/2, times 3/2, all the way till you'll get to the 10th term, which does in fact end up being this precise answer. The 10th term in the sequence is 307.55 as they rounded it to the nearest hundredth. If you want to test this theory, like I said, go back up to example 2 and just multiply all of these numbers, really starting after 40.5 technically is what you should do. Multiply by 3/2, 3/2, 3/2, and so on until you get to the 10th term. The 10th term will end up being this. So explicit versus recursive formulas are way easier to work with in the sense that I don't now need to know the term before 10 to find the 10th term. I can find the 10th term now by just plugging in 10. I don't have to know the 9th term. Here, I would have to know the 9th term. I could find the 100th term right now. If I wanted to find the 100th term right now, I can plug in 8, I can plug in 3/2, and I can plug in 100, obviously giving us what, 99. So whatever you want to test this as, you can do it on your calculator later, but 8 times 3/2 raised to the 99th power is the 100th term. And I wouldn't play around at all with the recursive rule if you're going to try the 100th term in this particular geometric sequence. And again, it is geometric because there's a common ratio. Okay, I'm going to ask that you read through example 4 on your own. As you read through it, of course, try to see on OneNote the completed version of the notes and fill in as you kind of continue through things. See if you can do some of it, but use the completed notes as a guide. And then example 5, do the same thing with as well. Do the best you possibly can. We will touch base on these items the following non-live day. But please try them out on your own, and that should hopefully lead nicely into your homework for tonight.